shows you that not all the
Can anybody else hear with you? Let's just test. Okay, no, Seth, they're here. I can confirm that now.
I see that. I see you all. In fact, I'm looking at, on my screen I have you rather than my presentation, so I'm looking right out at you right there. It's not a secret we're in the midst of an information processing revolution based on optical and electronic communications and electronic computation. But it's not clear yet that this revolution has a greater effect than the previous information processing revolution, which was the invention of full type for books. And indeed, that information processing revolution, the invention of books that movable type, is certainly not necessarily greater than the invention of writing itself. And writing itself is perhaps a lesser revolution than the invention of language. And language, which stems from the invention of, if you like, or the evolution of the brain, which itself was an amazing information processing revolution. And if we go even further back, the brain couldn't have come into existence were it not for the origins of life itself, which at bottom, as we've learned in the 20th century, is a huge information processing revolution in which information is stored on DNA and processed via reproduction and natural selection. Okay, so you can see that the world is this history of information processing revolutions, in which the one that we're relying on here for our connections between Emil's office at MIT and your fab in India is only the latest. Now, each of these information processing revolutions relies and goes beyond the developments of the previous one. Now, what is the origin of all these information processing revolutions? For instance, where does life come from? Life seemingly only began, at least on Earth, on the order of 4 billion years ago, but the universe is 13.8 or 13.7 billion years old. What was the previous information processing revolution? And my claim is that the original information processing revolution began with the Big Bang. And indeed, as soon as the universe began, it began, as it were, to compute. The universe processes information. Every elementary particle, every photon, every electron, every atom stores bits of information. Whenever two electrons or photons come together, bounce off of each other, they process that information. The universe effectively computes. It's a gigantic information processor or a gigantic computer. And that is the original information processing revolution. From which all subsequent ones, such as life, brains, language, writing, and electron computers, flow. So all our subsequent information processing revolutions come out of this original information processing revolution, which began with the Big Bang, with this computing universe. And when we build things like quantum computers, which is what I and Neil and lots of other people, I see people there who do that as well, what we're doing is we're effectively hacking into the universe. We're hacking into the universe's information processing ability. We're turning that information processing ability to run programs that we ourselves like, for instance, making a little quantum computer run Shor's algorithm. That's something we'd like to hack the universe to do. So that's the message, the overall message of this talk. And so if we get cut off right here, I just wanted you to know that before we go into any other slides. So are there any questions at this point? Does anybody want to make a comment? I would really enjoy having some questions from people on that other side of the...
Uh-oh.
Okay, if you don't ask any questions, then I'll just go on to tell you the stuff that I plan to tell you.
We have one question.
Charles?
Charlie, great. I knew I could rely on Charlie.
I'm a little bit afraid that in the 19th century, people would say, or the 18th century, that the universe has been a giant steam engine ever since its beginning. Are you not now describing what people have always known in the most latest fashionable language?
Absolutely, I'm certainly open to accusations of that sort. Indeed, you know, this metaphor of things as machines, which was a very powerful metaphor, and essentially drove first the Enlightenment with its creation of modern science in the West, and then the actual creation of machines in the Industrial Revolution. This was a very powerful metaphor. And so, of course, for instance, at the beginning of Hobbes' Leviathan, he talks about the human body as if it were a piece of clockwork. So he had a machine that he knew, a clock, and he said, oh, well, you know, the heart is like the pendulum of the clock, and the muscles are like the wires that bring force from the weights, and the gears are like the brain, etc. So naturally, in talking about the universe as a computer, I'm guilty of the same kind of metaphorical talk that people like Hobbes and then everybody else for the next 300 years were guilty of. However, so the point is very good. But however, I would actually like to claim, and let me give the evidence for it now, that in fact people have known this, that the universe effectively computes, that every atom registers information. People have known this for almost 150 years, for long before the invention of digital computers. And indeed, the basic ideas of information and information processing, that is, the notion that every atom stores a well-defined number of bits, and the formula, the mathematical formula for information, to describe the number of bits atoms register. These were developed in the latter part of the 19th century by people like James Clerk Maxwell, Ludwig Boltzmann, and Josiah Willard Gibbs. Indeed, the people who founded statistical mechanics were, in fact, the people who worked out the formulas of information theory, realized that all atoms register bits, and developed equations, such as Boltzmann's equation, that describe how that information is processed when two atoms collide. So, even though I'm guilty of this of using a metaphor for computers as a popular thing and describing the universe as that, I also claim that in fact there's very solid science that shows that this is the case, and that is that the universe is processing information at its most microscopic levels. And this science existed long before anybody had notions of electronic computers. I don't know that Boltzmann and Gibbs and Maxwell knew very much about early machines like the differential analyzer, right? So they were certainly not guilty of thinking the world a computer when they came up with the formulas show that it is. And as an example of this, let me point out this picture here, right here. This is my drawing of Boltzmann's brain. Now, you can actually go and get a picture, a photograph of Boltzmann's brain on the internet. It's not hard to do. And it actually shows a picture of a frowning, somber-looking Boltzmann over a reflecting pool. But the formula engraved on the grave on the stone is the same. That formula is S is equal to K log W. Now, what does this mean? Well, this is a formula. In this formula, W is the number of microscopic states of a physical system, what Planck called the number of elementary complexions of that system.
Yeah,
Log is just the natural log, the logarithm, is 2.
I think we have a
And K, yeah, just a second, let me finish, Charlie, then I'll get the question. And K is Boltzmann's constant. Note, actually, that this formula was actually first written down by Planck, not Boltzmann. And this constant K, which we call Boltzmann's constant today, originally was called Planck's constants by the aerophysicists. So Boltzmann, who actually committed suicide in 1906, shortly after visiting America, I don't know if there was any connection. I wonder what he would think to have another man's formula on his grave. Charlie, go ahead. This is the 100th anniversary of Boltzmann's death. So if you just change a few digits there, that might still happen. Let me knock on wood here if I can find any wood in Neil's office here. Okay.
Okay, so Seth, carry on.
Go ahead, sorry.
Absolutely, no, please keep heckling me. Other people heckle me too, I like that. I love being heckled from the other side of the world. So, and if you look at this formula, we see that the real formula there, what we're looking at, is a formula that was later developed by that information is minus the sum over the different states of p sub I log p sub I, a quantity that Shannon called H in his famous paper. Why did he call it H? Because when he went to John von Neumann and said, hey, I found this great quantity that measures information, what should I call it? Von Neumann said you should call it H, because that's what Boltzmann called it. Right? Actually, Boltzmann called this minus H, which led to a lot of confusion later on. But the point is that the basic formulas of information theory developed in the end of the 19th century by people who had no notion of electronic computers. And the notion that information was processed when two atoms collide is in fact the basis for Boltzmann's equation. Indeed, Boltzmann's equation is a way of analyzing what happens to information when two atoms collide. And Boltzmann's equation essentially says when two atoms collide, they attain mutual information about each other, and so their individual entropy increases. So if they're in a case where you know more about them to begin with, and then they collide, then you know less about them afterwards. And that's the basis for entropy increasing in Boltzmann's equation. Boltzmann's equation is a statement about information processing. Okay? So this whole notion of the universe is effectively computing is an old one. That's what I want to say. And I'm just saying it again in language that we can understand. All right, are there any more questions at this point? Okay, good. Yes, I noticed that when I put my finger out like this, it gets closer and closer to the camera there. It looks rather ominous from this end, so I don't want to intimidate people from doing this. Let's go on. So what does this mean in the case of something like an atom? So Boltzmann, in the case of an atom, he essentially said they didn't know about quantum mechanics back then. It wasn't until Planck figured this out right at the turn of the 20th century. So they essentially said, oh, well, let's suppose that we have some atom that's moving along. Here's its position, and its position is only defined to an accuracy delta x. Well, then, the number of effective states of this system is essentially the logarithm of, well, the number of effective states is the range x divided by delta x. And the information in this position is just the logarithm of big X divided by delta x. That's the number of bits that's registered by this atom. Okay? Now later on, Planck came and showed that indeed there's a natural scale in phase space given by Planck's constant. So if I have a range x for position and p for momentum, then there's a little range, Planck's constant, which is delta x times delta p. And what you see is that the formula for entropy is just the logarithm of the range in x times the range in p divided by Planck's constant, delta x, delta p. Planck, of course, originally used quantum mechanics to try to resolve a question about entropy, which we now would realize is a question about quantum information. He wanted to show that the amount of entropy emitted by a black body, such as an oven, that's emitting hot radiation, that this entropy is finite, because if you calculate it classically, it's infinite, both the entropy and the energy. And he was said, oh, well, maybe if somehow energy is discrete, if energy levels are discrete, then entropy and energy will be finite. And indeed, that's what he showed. He used the fact that if energy levels come in discrete chunks, so photons can only take, well, in fact, he made a notion of if light comes in discrete chunks called photons, then energy levels are discrete, and the amount of energy that comes out of a hot oven is finite. And so you can see that Planck was actually making a statement about statistical mechanics, but about information, about entropy. So indeed, quantum information, as we know today, even if it's trendy, it has its origins mathematically back at the very beginnings of when quantum mechanics was developed. So quantum information goes back to the very first paper that was ever written on quantum mechanics by Planck in 1901. Okay? And indeed, of course, now we know shortly thereafter, people like Bohr started analyzing atoms and said, hey, look, the energy levels of atoms are discrete. So the energy levels in electrons, the energies of electrons rotating around atoms are in fact discrete. And if we just look at the ground state and the first excited state, then these can form a bit. So atom and the ground state, Bohr didn't say this is what we say now, people like Charlie and I and me.
Seth, I have a question. Did Szilard think about quantum mechanics
famous paper on the gathering of entropy by intelligent beings and on Maxwell's demon. I don't know that if he was actually he had a quantum mechanical model in mind. Charlie, what do you think?
I don't think there's a mention of quantum
Because the
mechanics
reason
in
I
that
ask is,
paper.
I mean, your spin is nice, but it also leads to a testable prediction, possibly about causality in Szilard's influences, which I don't know anything about.
Oh, I thought you were going to talk about David Deutsch's notion of time travel via entanglement. So perhaps you could, these ideas were implanted in their minds via some errant time machine. That's also possible.
The question is, did Szilard write his paper with information in quantum mechanics kind of in the air, or did he detour around it and follow Maxwell and Boltzmann?
No, in fact, the notion of applying information to quantum mechanics was missed by all sorts of people. I mean, you would think that von Neumann, of all people, having written, his groundbreaking textbook on quantum mechanics, would have, and also be one of the founders of information theory and statistical mechanics, would have thought of quantum computers. But as a number of people, including Charlie, have pointed out, he evidently didn't think about this. I read his collected works, and in none of his published works, or in any of the works collected in his collected works, is there any information or mention of quantum information? It
Ike, can you hear me?
Like, yes, Neil.
Do you have a presentation?
I do. It's on a memory stick, and we'll just put it on this laptop here.
No, that laptop isn't running the VNC. The VNC is on the server. That's just running a web browser to it. If you can't run a VNC server, you need to email it to me, and I have to put it onto this server.
Okay, I'll try to run a VNC server here for you. It'll probably be easier.
Quickest would be is if you can quickly install type VNC and tell me an IP address, and then I can add it to the conference. Okay?
Understood. Give me 5 minutes. Yeah. See, there we go. This is what I'm talking. You know, the universe is out of control. And why is it out of control? Because of all this new forms of information processing. Okay, so let's go on there. While Ike tries to do this magic, which I'm glad it's not me, is all I can say. I'll look at him every now and then. I'll tell you if he's sweating or not. Okay, so now let's look at different ways of hacking the universe. What
Is
Well, I'm not done, but
Oh.
yeah, please.
Is the belief that the universe is fundamentally described in terms of information a career-ending black hole?
Yeah, good question. Yeah, well, a few years ago, inspired by one of my favorite computers, which ended its life as a black hole, I decided that it would be interesting to look at whether black holes could compute and how they compute. Let me actually just go on to the next slide, because this is related to this. So, in fact, let me use Neil's question to, I'll get to this in the transcript aside after this, but let me just talk about this for a second. volume of space-time, that at a certain point something happens. Then what happens is, this volume of space-time becomes a black hole. We've crammed too much energy in it, and light can no longer escape. Now, I have nothing against black holes. As I said, my favorite computer ended its life as a black hole. But if part of your GPS network becomes a black hole, that's bad. You can no longer measure the volume of space-time, measure the geometry of space-time within that volume, because that part of the GPS network can't even communicate out any longer. So the information about that volume of space-time is now lost to you. Okay? So we have to keep the energy density lower than the Schwarzschild limit. The Schwarzschild radius is 2gm over c squared, which is equal to 2ge over c to the fourth, using Einstein's famous formula E equals mc squared. This implies if you put this bound on the number of ticks and clicks from the Moragoulas-Levitin theorem together with the Schwarzschild bound, then the total number of ticks and clicks, the total resolution to which you can map out a volume of space-time, is limited by the spatial extent times the temporal extent divided by a resolution. But the resolution now is not just the quantum scale, but the Planck scale, the Planck length times the Planck time. In other words, at this factor of 2 pi. So the total number of ticks and clicks you can cram into a volume extent x of length t is limited by this area divided by 2 pi times the Planck scale. It's an interesting result. It's closely related to and consistent with the holographic bound that puts limits on the number of bits you can cram into some volume. But this limit actually implies, notice that I derived this without having to apply to quantum gravity or anything like that. This is simply a limit on the quantum mechanics of measuring space-time combined with a reasonable demand that my measuring apparatus not collapse, undergo gravitational collapse. Okay? So this quantum geometric limit is not a limit of quantum gravity, or is not derived in quantum gravity, though one should hope it would apply there. It was derived simply by applying the normal physics of measurement to the normal fit to a reasonable demand on how we measure self-gravitating systems. Now, if this does indeed apply to gravitational systems, and indeed I would certainly hope it does since it's so simple to derive, then we actually have to make statements about the universe as a whole. In particular, the total number of ticks and clicks, the number of elementary events that can be crammed into the universe as a whole, is in fact less than the age of the universe, 13.8 billion years, squared, divided by the Planck scale squared, which is around 10 to the 122. Only about 10 to the 122 elementary events, ticks and clicks if you like, or collisions of atoms, or flips of bits, can have occurred since the universe began. This means that the resolution to which the universe is actually mapped out by the matter within it is far less accurate than that normally thought. Normally people think, oh, it's the Planck scale. In fact, it is not. The resolution on average to which we map out the universe is about 10 to the minus 5 meters, 10 micrometers. You may say, well, heck, I can measure distances much shorter than 10 micrometers, and indeed you can, but only by putting a bunch of physical apparatus in there. And by you concentrating matter to measure things more accurately here on Earth, out there in interstellar space, where the density is less around 1 hydrogen atom per cubic meter, and the only stuff that's measuring the geometry of interstellar space is the cosmic black body radiation, which has a wavelength of this, right, a few centimeters, then out in interstellar space, the geometry of space-time is much less well-determined than it is here on Earth. And if you'd like to find out how you can make this idea into a full quantum theory of gravity, I urge you to check out my paper, A Theory of Quantum Gravity Based on Quantum Computation, which is on the Los Alamos Precursor. Okay. I've gone
you are saying essentially that the universe is a non-trivial dynamical process when you say that it's a computer. And I wonder, I think that's we would probably all agree with that, and maybe even Maxwell and Babbage would have agreed with it. But I wonder if you want to become more quantitative than that, are there incomparable kinds of computation? I think probably not. Computational universality means that any computer can simulate any other. But I wonder if there are kinds of natural processes or kinds of dynamics that are perhaps mutually hard to hack, or one can hack the other but not so easily the reverse. So that to build up some kind of partial order of computational complexity of the dynamical processes in physics.
Yeah, that's a really good question. Yeah, so indeed, what is known is that if you have local interactions between quantum systems, and you can control those local interactions, then first of all, any such system can be a universal quantum computer, and also any such system with controllable interactions can effectively, efficiently simulate any other system with local interactions. However, if you have systems that have global interactions, well, and also at bottom we believe there's strong evidence that the laws of physics involve local interactions, so maybe that's all that is. But certainly, at the scale of building devices in the laboratory, in the time scales and length scales that we have systems that have large, long-range, non-local interactions, and it may be very hard or exponentially inefficient to take something that has very long-range interactions and to turn it into something that looks local. Indeed, it would be quite interesting, I think, to try to give an example of such a system where that can't be done. Let me actually just say, since you brought it up, there is one thing, one prediction, if you like, or this is prediction in the sense that people in the quantum gravity or string theory world use the word prediction, which really means a retroviction, okay? So one feature of the universe that its computational nature explains. So let's suppose that the universe is, in fact, a universal computer, not merely a non-trivial information processing system, but capable of universal computation. Indeed, since universal computation is ubiquitous,